Okay, welcome in everyone. So today we are continuing our work on arrays and hashing. Spoiler, today is actually really just an array problem. There's not a hashing element to it, but we are looking at product of array, or I guess it's products of array except self. Little medium problem here. So we'll read through it, do a little diagramming, and we'll go through, I think, two solutions. We'll do the naive solution as well as an improved solution, and then we might even, if we have time, iterate on that. So let's see. Okay, so problem says, given an integer array nums, we want to return an array output, where output at index I is the product of all the elements in nums except nums I. So if you're looking at the 0th element, you want the product of everything but element 0. Okay, and each product is guaranteed to fit in a 32-bit integer, so we don't have to deal with weird overflow problems or anything like that. Then the follow-up here, so we'll do both the naive solution and the follow-up. Could you solve it in O of n time without using the division operation? So I hope so. Ivy just mentioned the visual's about to go crazy for this one. I think the first time I explained this one to someone, I did not do great on the visuals, so hopefully it's better this time. So they sort of spoil it in the follow-up here that you can just use the division operator to make this problem sort of trivial. You can just find the product of the whole array and then just divide it by whatever number you're looking at. So, for array 1, 2, 4, 6 here, the product of the entire array would be 48. And to get each of the entries, you could just do 48 divided by 1, 48 divided by 2, 48 divided by 4, 48 divided by 8, with some exception somewhere for 0 being present in the array. So division sort of makes this a boring problem, as well as the start of this, or the naive solution for this, we can do it very intuitively with greater than O of n time, specifically O of n squared time here. So the follow-up is the interesting part, just FYI. But let's take a look at the examples. The first nums array we're given is 1, 2, 4, 6. So again, if you take a look at each of these individually, at index 0, we would multiply 2, 4, and 6 to get 48. At index 1, we would multiply 1, 4, and 6 to get 24. At index 4, we would multiply 1, 2, and 6 to get 12. And then at index 3, we would multiply 1, 2, and 4 to get 8. So actually doing these calculations is not super tough. They give us an example with both a negative and a 0 here. So with this guy, 0 times the rest of it is 0. When we cut out the 0, it's negative 1 times 1 times 2 times 3, which is negative 6. And all the rest of these end up being 0 because 0 times anything else is going to be 0, right? Okay, some constraints were given. The length of the nums array will be between 2 and 1,000. And then the individual elements will be between negative 20 and 20. Okay, so let's do a little diagramming. Let's take a look here. We'll do 1, 2, 4, 6 here just because it's pretty easy to work with and the numbers aren't too wild. So the naive solution is very straightforward here. We could just say, hey, for whatever index I'm on, go ahead and go through the entire array and keep a running product. Just make sure you don't multiply the current element that we're looking at into the product. So, we would have our results array. And when we're at index 0, we would, here, I'll say I equals 0. And product, when we start, we're going to initialize it to 1 because that's the multiplicative identity, right? You multiply something by 1. It doesn't change it, so this is a nice place for us to start in terms of initializing that product. If this were a sum, we would initialize it to 0 because adding on to 0 doesn't change anything. So this time it's 1 because we're multiplying. Okay, so all this to say, we're going to have another pointer that goes through the entire array, and when the index of that pointer matches the one that we're trying to calculate, we're going to ignore it. So if I equals, I guess j equals 0 currently, right? So I equals 0, j equals 0. Since these are the same, we'll skip it. But at other times, so for every other one, we're going to go ahead and multiply by 2 in this case. Multiply by 4. I guess I'm not going to write j equals 0. Y'all know how that works. J equals 4, or that at index 2 we have 4, so we now have 8. So we're just multiplying the current product with whatever's next. We get 48, and once that pointer gets to the end of the array, there's the product that we need to include. I'm not going to do the rest of that because y'all, I hope by now, well, you know what, maybe we'll do one more loop just so that we can get some contrast on matching the arrays. Okay, so we initialize the product to 1 again, right, because we've started the next loop. This time, 0 and 1 are not the same index, so we can go ahead and say, hey, go ahead and multiply that by 1. Well, nothing changes this time, but no big. Okay, now the index is matched, so we can ignore this element, multiply it by 4, multiply it by 6, and then we get the next entry, right? So not super tough to do this set of calculations here, and the naive solution is pretty easy to code. In fact, we'll just do that real quick here, and then we'll talk about, hey, how can we improve this? As I'm doing this, or I guess before we actually do the coding, this is, well, you know what? No, we'll code it first, and then we'll talk about the time complexity for this naive solution. So we can say for I in range len nums. Whoop, okay. And then we'll say for j in range len nums. Okay, actually, before we start this inner loop, we'll say product equals 1. And then we're going to need a results array. Okay, so now that we got these loops set up, we're going to say if I and j are the same, we can actually just continue. So, wow, actually, I don't know if we've used continue in any of the examples so far. So continue just means go on to the next loop. It doesn't, so this is in contrast to break, which says stop looping. Continue just says go ahead and do the next one. You don't have to do the rest of the stuff in this code block. So if I equals j, we'll just continue. We don't need to multiply it in. But otherwise, we're going to go ahead and say product times equals nums j. And once we've multiplied all the numbers in, we can say go ahead and append product. Okay, and once we've done all of those, we can return results here. I probably messed something up. I tend to mess up simple solutions. Okay, great. So it worked. I was like, where's all the details? Okay, and then obviously this does work, or we'll see if it does work for everything, and it sure does. Okay, so let's talk about the time complexity. We've got one loop that goes through all of the elements once, and then every time we look at an element, the other loop, so the j pointer, is going to go through all the elements. So for every element, we look at n elements, and there are overall n elements. So this is going to be n times n, which gives us n squared time complexity. So from the follow-up here, obviously we can achieve O of n time, and we don't want to use the division operator. So how can we do this? Well, we need to have some way of collecting the subproducts, right? Here's kind of the core of what makes this problem tick. There's a bunch of calculations that we make repeatedly, right? So the first time we do 2 times 4 times 6. The next time we need 4 times 6. The next time we need 6. And okay, let me actually diagram this a little bit better. And I'm actually going to use a little bit of color coding for this. So for the first element, there's nothing to multiply in front, so maybe we can just say that there's a 1 there. But for the second, or sorry, for the back part of that, we need to do 2 times 4 times 6, right? In fact, let me, how do I want to color code this? Okay, I'll do the back part in blue here. Okay, and then when we look at 2, what we need is like 1 times 1, and in the back, what we need is 4 times 6, right? And then in the front we need, well, I'll just leave this. Let me think. It's like this one, sorry, let me clarify. This one is just sort of like that's the multiplicative identity. I'm just going to leave it there. It's not really part of the data, but maybe I'll phrase it this way. There's going to be a 1 just kind of bookending the content here. Okay, so for the second element, we need 1 on the front. We need 4 and 6 on the back, right? For the third element, we need 1 and 2 in the front, and in the back we need 6. And then for the last element, we need 1 and 2 and 4, and then in the back we just need 1. So there's these repeated multiplications, there's these subproblems that keep being developed as we go, and hopefully there's a little bit of a pattern emerging if you're looking at these numbers. We need what we refer to in comp sci as prefix and postfix values. And that means we're literally looking at the stuff that comes before and the stuff that comes after. We would like to reuse those numbers if we can. For example, here, when we calculate 1 times 2, we don't want to have to calculate 1 times 2 again the next time. Like, we already have that number. We would like to just use it, right? Okay, so that's the motivation, or that's what leads us to think maybe there is actually a more linear solution to this. So how exactly we're going to do that? I'm going to use a few. There's several ways we can approach the loops here, but let me actually give us a longer array. So this is a little bit more obvious, kind of where things are coming from here. So if you have 1 times 2 times, or 1, 2, 3, 4, 5, 6 is our array. Here's what I'm going to do is I'm going to have, well, so here's nums. I'm actually going to label these. I'm going to have a prefix array. I'm going to have a postfix array. Ooh, am I going to spread this out more? I think I'm going to spread this out more because there's a lot to capture. I'm going to say 1, 2, maybe we'll just do like 5 elements. Okay, prefix array, postfix. Actually, do we need all that? Do we need all that? Let me think about this. Yeah, we'll include it for now, and then... Well, the division solution isn't, like I said, it's not super interesting. You just calculate the product, and then you just do your divisions. So I'm going to leave that to the reader to calculate. I trust you guys to do that. Maybe post that solution somewhere if one of y'all gets to it. Postfix, and then we also need the results array. Let me think about this though. Do we need the extra array? I think we can do this without the additional arrays. Let me just like stew on that for a second here. Yeah, I want to say we can do it without. So rather than these arrays actually, yeah, we'll just do the results here, but we'll color code it. Oh, okay, let me think. Sorry, give me a second to chew. Hold on. Y'all are yelling at me. Don't yell at me. I just need a second. Should we use the extra space? We might. You know what? I'll include them, and then if we realize we don't need them, you know, they're just there. We haven't coded anything. We lose nothing by doing this. Okay, so here's the thought, is we can start by saying, we'll start at the beginning of the array. We'll say, hey, what is the product of everything that comes before the element that we've seen, or that we're looking at right now, right? Obviously, when we start this, the answer is, well, there's nothing there. You could just think about multiplying by 1 because that does nothing, right? Now, when we get to the next element, what we can say is, or to get the value of the next part, again, what we're trying to figure out here is, what is the product of everything that came before me, right? Well, we can actually figure out the next thing by just taking this, multiplying it by that, and putting it right here. This tells us the answer for what's the product of everything that comes before 2, right? Okay, and if you want to know what's the product of everything that comes before 3, we'll just multiply this, and you'll have your answer. Let me actually just color code this all in red. Now, what we're going to do shortly is we're going to take this and we're going to require less space, but this overall isn't too bad, and we'll continue this process. So 2 times 3 is 6. 6 times 4 is 24. And what this array captures is, here's the product of everything that came before the number that I'm currently looking at. And you can check this for me. But in fact, let me think about this. Yeah, no, this is good enough. I was going to say maybe we'll even write it out, like what were the things that got multiplied to get us here. You know what? Yeah, we will. No, we're good. Surely you guys understand what I'm saying here, right? Surely that, like, is... Yeah? Okay, great. I was like, we could diagram this more, but I don't think we need to. Okay, so, again, we go back to our original problem. One question we're trying to ask ourselves at all times is, what is the product of all the numbers before me? The other question is, what is the product of all the numbers after me? What? You know what? Figure it out then. Okay, so now we can do this again, but just from the back. From the back, you say? Freaky ass. Okay, so we'll do it again. We'll say, okay, I'm just going to put a 1 here because when you multiply by 1, it doesn't change anything. That's quite nice for us. And then now, to get the element before me, we just take the current entry, multiply it here, and that gives us, again, what we're saying is, what's the product of all the things after me, right? I feel weird that there's not a circle here. Well, I guess, yeah. We don't need... Okay, anyway, sorry, that's not the point. Okay, and then again, this times that is going to give us 20 here. And again, this answers the question, what is the product of all the things after me, right? And notice we're not repeating any of these multiplications. We just do it once, and we can use the result of what we just used a second ago to find the next entry that we're looking for. This is actually probably something like dynamic programming, which is where we kind of record subproblems and use them in future iterations. We'll have a whole section on dynamic programming later, but this is actually sort of the nature of it. Okay, so I'll finish out the example real quick. 20 times 3 is 60. Again, this is the product of everything after me, right? And then 60 times 2 is 120. And that gives us most of the data here. To get the results now, all we've got to do is multiply these to get the results. Again, what each of these represents is what's the product of everything before me, and then what's the product of everything after me, right? Great, and that's, I feel weird that these are not, I'm gonna just, I'm sorry. I was about to say, this is something you shouldn't say. I was about to say I'm very OCD. Don't say that. But I was going to say also, I realized over the last year, I think I actually do have like a counting compulsion. It's nothing crazy. It's not affecting my life. But I was like, I thought everybody was doing that. Isn't that like a thing vampires do, right? Isn't that like they have to count? They're like, I got to count the toothpicks that you dropped or whatever. Anyways. Okay, and this is actually the solution. We'll code it and then we'll see if we can optimize it. As I understand it, all like the big optimization is you can optimize for space, but in terms of optimizing for time, I think the only way you can like do that is to fit everything into one loop, where you do 2 things in that one loop. But that's just the same as doing 1 thing in 2 loops, so we won't bother too much with like the 1 loop implementation. What counting compulsion? I'll count my steps when I'm walking. I'll count my steps in groups of 8 in my head. I don't know. Is that weird? That's weird, right? Yeah, just random counting. I don't know. I am a freak. Yes, exactly. The blocks of concrete. Anyways. Okay, let's code this out. We'll use the extra space for now, and then we'll optimize for space right after that. So here's what I'll say is, so we have nums. Oh, that's not, okay. Anyways, I'm going to say we have pre and post. And these are both going to be, surely there's a way to do this. Okay, well, here's what I'll say, and I'm going to arbitrarily make it like 1 times len nums for both of these. 1 is safe because if we multiply by it, it doesn't break anything. We could also use maybe like -1 for the rest of the entries to say like, oh, by the way, this is an invalid entry. We haven't used it yet, but it's a pain to code that, so we won't do that. We'll just say, hey, I need an array of 1s for both pre and post. I can't look at chat right now. Okay, so now we're gonna go forward through the array, I'll say for I in range len nums. Let's actually consult the diagram because I be forgetting. So for I in range len nums, what do we need to do? We'll say, oh, well, actually, this is interesting because when we get to the end, we don't need to do this, right? So maybe we could say for I in range like 1 to len nums. Also, like there's nothing to multiply in for the first entry, right? And then also we don't. Yeah, no, we're good because we're never. I was gonna say, okay, sorry. Here, let me explain what I was thinking about. If we just did this for I in range len nums, what we would have to do is we'd have to multiply forward, right? So like at index 0, we would have to do something to calculate index 1. The problem is when we get to the end, that's gonna like get messed up because we would be looking, or we would be trying to set something after the end of the array. So we could either do that and just reduce this by 1, or we can start at 1 because, right, like the first index here is always, we don't have to do anything to it, and then we can just stop at the end. So what we're going to do is we're going to set the number before us. Or sorry, we're going to use the previous number to set the current number. So either way, you know, this is something you can do. If you'd like to do it the other way, that's totally fine, but we'll do it this way. Okay, so for any particular index we're at, what we need to do is fill prefix at that index with the previous entry times the current entry from nums, like the actual number we're looking at. Okay, and I think that's it actually. So again, well, actually, let me comment this because that's a good practice to be in. Every prefix product is the previous one times the current entry. Okay, hopefully we agree on that. And then now we're going to do the same thing but backwards. So now we can say for, well, actually use I again, but I'm going to use J. For J in range, I hate doing this actually. Well, we're going to start at len nums minus 2, because len nums minus 1 would be this, but we don't need that. We want to start here. So I'll say len nums minus 2, and then again, this -1 means go backwards by 1 and stop when you get to the beginning. Okay, and same concept here. Every postfix product is the, well, it's weird because is it next or previous? So I'm just going to say previous one again, times the current entry in nums. Maybe we should say that. This isn't a super necessary comment because I just said this. We're doing the same thing, but you know, just so we have that as a guide. So I'll say post at index j is going to be post at index j plus 1 times nums at j. Okay, and then to get the result, all we have to do is multiply those. So here's what I'll do is I'll do a list comprehension. I'll say return this list where each entry, so for k in range len nums, maybe we'll say, what we need to return is pre at k times post at k. Okay. So I think that's it. Let's find out. Does anybody want to call it ahead of time? No, list comprehensions are so nice. Look how legible this is. You just have to read it backwards. So for every index in the length of nums, right, just multiply whatever's at pre and whatever's at post in those places. This is so lovely. I used to hate list comprehensions because I just thought they were scary, but yeah, okay, let's run it. Does anybody want to call it though? Have I messed something up? Oh. Ooh. What did I do wrong, you guys? Is it len? Maybe it is. Maybe it is. No, it's not, because then we couldn't add 1 to it. Wouldn't that break it? You know, like we have to start. Well, this is a great time to diagnose. Uh, yeah, let's take a look at it. Well, actually, so this is a great moment because one, I will mess more stuff up in the future because these problems get harder. But two, if you're in an interview and you mess something up, that's fine. Part of what they're trying to figure out is how you diagnose issues and how you hopefully go about solving them, right? And if you really get stuck, and I will probably do this to you guys at some point, ask for a little bit of help. Your interviewer is not expecting you to be perfect, or if they are, maybe you don't want to work there. So, anyways, let's take a look. Um, yeah, I'm pretty sure we want to start. Well, okay, let's actually take a look at what we did get. Um, right here we got 8, which is 2 times 4. Right here we got 16, which is 8 times 2. Okay, what's going on here? Pre at I equals pre at I minus 1 times nums I. Pretty sure that works out fine. Let's actually see what pre and post look like. Yeah. Well, I'd like to see just like what the contents are. Oh, that's not at all what I was expecting. Was it? Hold on. 1, 2, 8, 40. So pre worked actually just fine. Post is. Huh? Oh, okay, hold on. J in range. Okay, yeah, so start post at J. Is that not right? Every post fix. Yeah, okay, so this is right. Post at J, and it starts. Do you have to push the num J? Oh, yeah. Oh, I've got this backwards, huh? No, wait. Oh, yeah. J plus 1. You're right. Oh, do you have to wait? Do you have to push the num J because it's back? Okay, wait. Let's take a look. Let's actually. And this is if you got a rubber duck before, this is where your rubber duck comes in handy. We should be multiplying things that are at the same place for these blue ones, right? So that's what we've missed is I've multiplied this by that, right? That's not what I want. We want these to be multiplied to produce that. And then these are multiplied to produce that, right? So I've got the number that we're trying to include incorrect here, right? I think. Yeah, pretty sure that's it. Okay, let's check it out. No, so I've still messed it up. Am I not thinking about this right? Hold on. So we start here, and we say to produce the thing here, multiply that entry times that number, right? To get the thing here, multiply J plus 1, post J plus 1 times nums J plus 1. No? Is that not correct? Help! Help! Okay, let's print this again. Take a look. The killer is escaping. Oh, you know what? I bet it's just. I think there's weird things happening here. Let me see the output. Oh, we got 48 each time? What am I doing wrong here? Why do we keep getting 48? I think like we've somehow intertwined pre and post. I think this is what's messing things up. I shouldn't have tried to be fancy. No, I've really just messed it up. You guys, what have I done wrong? Oh, oh. Oh, you know what? No, am I realizing something? Wait, let me think about this. Yeah, we're gonna have to just go through the loops, you guys. Okay, yeah. It's so interview core. Okay, so here's what should happen for this array. We got 1, 2, 4, 6. Is this what we're expecting to have for pre? That's one question. No, yeah, this is not correct, huh? Oh, you know what? You know what? I was so focused on post not working, I didn't even realize pre was not working. Okay, so is post correct? Post is actually correct now. Pre is the thing we needed to fix. Okay. Yeah. And it's sort of the same issue, I think, actually. This was also supposed to be nums on -1. Okay, so I actually was on the right track. I just forgot to look at the other array. My bad, y'all. So I actually made the correct conclusion earlier, which is, hey, actually, by the way, to make these calculations, like if we're here, you look at both of the previous entries, right? These should get multiplied to make this. These should get multiplied to make this. So my bad, my mistake, and people make mistakes, right? Okay. I'm going to keep printing just in case we've messed something else up. Okay. So yeah, this is actually, if you got a rubber duck at Week of Welcome, this is exactly what the rubber duck is for. You need to explain what is actually happening in your code and see if it actually works. If you don't have a duck, come to our next GBM 2 weeks, well, 13 days from now. We'll give you a duck, okay? You guys are my rubber duck right now. I actually have like 3 rubber ducks on my desk right now. Okay, let's go ahead and submit this, and then we will very quickly talk about how we can space optimize this. So the thing is, we actually don't need the pre and post arrays. We can get rid of them if we store them in the results a little bit more nicely. Because when you think about this, like, why did we need to store all these extra numbers when we could have just multiplied them in right here? You know what I'm saying? So we don't need to keep them once we've got the numbers. You can just store them in the results array and then multiply by whatever it is that comes after, right? So here's what we can do is we can say, actually, I'm going to go ahead and initialize results to be 1 times len nums. So again, an array of 1s that is the same length as nums. And then we can do these 2 loops, but instead of trying to do all this, we can just say, hey, actually, let me not delete that because I'll cry if I forget how it works. The result index I, let's go ahead and, whoa, you know what, actually, hold on. We need to both store the prefix so far and put how much of that prefix we've got in the correct index, right? So we'd have to say something like results at index I times equals, so I'll say pre and post are just going to be 1 and 1 now. So results at index I, go ahead and multiply it by the prefix so far. And then go ahead and multiply pre by that. Right, so this way we can accumulate that product and just store it in a single number, because once we've calculated part of the subproduct, we don't really need it again. We can just use whatever the result was last time as part of the next product. Okay, so we got that, and then we can do sort of the same thing here. we can say results at j times equals post, and then post times equals result at j plus wait, is that right? Because this time results actually has, oh sorry, not results I minus 1, nums I minus 1. I was like, isn't results accumulating stuff here? Yeah, we need to just take a look at what the entry at that other spot is. Okay, and then now, instead of having to multiply the results, everything's already been accumulated in those results positions, so we can just return, oh, actually just res here. We don't need to do a list comprehension. Okay, I think that should work. Yeah, I guess we're gonna find out. I'm gonna cry, you guys. I'm going to cry. What have I messed up this time? It's like almost completely correct, but for some reason some of these things are backwards. We're having weather. I think now your post loop. I don't know what that means. Let's think about this. So, well, let's actually work through the example. This is stressing me out though. Wait, why did this not work? Yeah, pre and post. Okay, wait. Let me just proofread myself for a second and then... Oh, do we? Well, shouldn't it do the same thing though? Because this is going to start at the end. Oh, yeah. So, actually, Ivy, you make a great point, which is we're losing that... Actually, well, let me think. Res j times equals post. Okay, so yeah, because the last element we can just multiply it by 1, which is totally fine. So then in this case, we can actually start this as 0 as well. So I guess the difference here is that this time... No, wait. That doesn't make sense either. Because this is going to put us on the last element, right? Multiply the result of that entry times post, and then include the last number. So this would have been the same thing, right? No, so that doesn't actually change it. I think we're going to have to go line by line, guys. I was so confident that this was exactly how it was going to work. Let me chew on it for just a second to see if maybe I can explain it or figure it out first. But maybe we should get rid of some of these No, I feel like this should have worked. Hold on. Let me think for just a moment. Then we return res. No, I feel like this is supposed to work. Oh, wait. I think this is not quite correct. Because, let's see, res I think it's this. Because what are we accumulating? When we start at 1, this should be I minus 1, huh? Start res equals. Yeah, sorry. Okay, so this is probably, in terms of interview practice, this is not a good way to interview. At this point, I definitely would have started doing some writing. Yeah, exactly. So here's our problem, though. So I've diagnosed it, which is maybe this wasn't the best way to do it. But when we multiply, when we're trying to accumulate something in the result, since we started this at index 1, what we're trying to set is the previous part of the loop, right? So it's actually probably better for us to do this time, and then just have this be I. So this lets us say multiply by the prefix so far, which when we start is 1. And then we can just now include the current element as part of the prefix product, right? Yeah. And then so same with this one. Maybe it's more intuitive for us to say just go ahead and start at the end, multiply, in this case, when we start the last element by postfix, which is just 1 to start with, right? And then include the element that we're currently looking at as part of the postfix product. That's probably the more reasonable way to do this. Okay, let's see if that worked. Oh, the sigh of relief that I just sighed. Okay, so we can do that. And then again, the one other optimization we can make here, which isn't, I wouldn't say it's truly an optimization, is we can just combine these loops. And you can say like this, and then you can say like res, lenums minus I, minus, is that correct? Times equals post. And then like post times equals nums, lenums minus I minus 1. See what I'm saying? Y'all catch the vibe? So this is like, it's not really an optimization because we're doing the same number of actions. It's just in one loop now. People love to be like, oh, but you needed 2 passes instead of 1. Well, ho, we gon' look at the numbers anyways. Who cares? Anyways, let's see if that worked. I just want to like see if it was correct. Oh, thank God. I needed 1 win tonight, please. Okay. So whether you do it in 2 loops, 1 action each, or 1 loop, 2 actions each, it's roughly the same. Great. So yeah, this is kind of a fun one. Diagrams, super helpful. I wish I had just really thought about what was going on in the diagram. That would have been great. Yeah, and again, part of this is like, in terms of the optimizations, part of this is like, if this was production code, I would prefer for it to be legible and understandable rather than clever, right? So like, it might have been better to use a little bit more space so that we can understand what the hell happened when we made the array, right? But this works as well. Either way, we get the right result. That's what matters. Okay. Any questions? Did we follow? Anything I can clarify? Yeah, 45 minutes isn't too bad given that we did like a few different solutions. Yeah, I guess your homework assignment is to go try the division one because that's really easy to write, and put that in the thread. Yeah, I know, homework, right? No, it should take you like a minute, y'all. The division solution is so easy. Please, come on. Okay, we're gonna call it there. If you have more questions for me, let me know. But otherwise, have a great night, and I'll see y'all for the last problem of the week tomorrow.